Hey y'all, today we're going to look at a couple new equilibrium constants. The equilibrium constant of water, Kw, the equilibrium constant of an acid, Ka, and the equilibrium constant of a base, Kb. We're going to learn how to convert between them and also learn how we use them in acid-base equilibrium problems. Let's go ahead and get started. The first thing to keep in mind is that K, just like any equilibrium constant, tells us the extent to which the reaction proceeds in either the forward or reverse direction. In the case of Ka values, the stronger the acid, the greater magnitude of the Ka value. So the larger Ka values, stronger acids. We only use Ka expressions to describe weak acids, though, because strong acids go to completion. They don't go to equilibrium. So the stronger a weak acid is, the bigger its Ka value. Conversely, Kb values do the same thing for weak bases. The stronger a weak base is, the larger the magnitude of its Kb value. Kw, as long as the temperature is constant, is always the same. And at 25 Celsius, the Kw is always equal to 1 times 10 to the negative 14th. So here we have two different positions with a Ka and a Kb that actually, if you look at them mathematically, multiply together to give you Kw. So on your formula sheet, you'll see Ka times Kb is equal to Kw. Let's look at the Ka and Kb values with the equations that they describe. A Ka value talks about the dissociation of a weak acid in water. When it dissociates into its conjugate base and H+. Or if you're using water on the reactant side, H3O+. This means the equilibrium expression, the Ka value, is the concentration of H+ or H3O+ times the concentration of conjugate base divided by the concentration of the remaining weak acid. The Kb value, same thing, except we flipped it to a base. So we have concentration of hydroxide times the concentration of conjugate acid divided by the concentration of weak base remaining. Finally, with Kw, it's the autoionization or dissociation of water, where we have H2O dissociating into the concentration of H+ and the concentration of OH-. Remember, water is a liquid, so we don't even include it in my equilibrium expression here. So the Kw is simply equal to H+ times OH-, which means when we do the manipulation of Ka and Kb, if you combine those two, thinking back to Hess's law of equilibrium, if you combine those two, you multiply them together, what we end up doing is canceling the weak acid, canceling the weak base, and we're left with the concentration of H+ times OH- equals the Kw, which means Ka times Kb equals Kw. All right, let's look at a practice problem. Here I've got lactic acid, a 0.1 molar solution. I know it has a pH of 2.44, and I need to use this in understanding to find its Ka value. I'm going to do this by setting up a rice table. If I know the original concentration of my lactic acid was 0.1, that's going to dissociate to some amount, minus X, and the conjugate lactate ion and the H+ ion are both going to increase by a factor of X. I know X because I know the pH, and I know pH is equal to the negative log of the concentration of H+, which means that the concentration of H+ is equal to 10 raised to the negative pH. So 10 to the negative 2.44 equals 0.00363. Therefore, I know that X is equal to 0.00363. This means that the amount of lactic acid that I have remaining is 0.1 minus 0.00363. The amount of H+ and conjugate base would both be equal to 0.00363. When I plug these into my Ka expression, it's going to be 0.00363 squared divided by 0.1 minus 0.00363. This gives me this gives me a Ka value of 1.37 times 10 to the negative 4th. So I know that the Ka value of lactic acid based off of this problem is 1.37 times 10 to the negative 4th. So now that we've figured out how to find the Ka of an acid, let's look for the Kb of a base. Remember, the Kb expression, the equilibrium expression, is a little bit different. the Kb expression is equal to the concentration of hydroxide times the concentration of the conjugate acid divided by the concentration of your original base. So when we solve for the Kb of this problem, ammonia, NH3, we know that we can go ahead and use this new equilibrium expression, which is on your formula sheet, by the way, Kb, to solve for it. In order to find the Kb, I'm going to set up a Rice table again. I'm going to solve for my equilibrium concentrations of both the ammonia, NH3, and for both the OH minus concentration and NH4 plus concentration. One thing to be aware of is I'm given the concentration of hydroxide at equilibrium is 1 times 10 to the negative fourth, which means that the concentration of the NH4 plus is also 1 times 10 to the negative fourth. Remember, when NH3 dissociates the water, when it hydrolyzes water, it creates 1 NH4 plus and 1 OH minus. So those are in a 1-to-1 ratio in this situation. We solve for those values, we plug them into the Kb expression, and we end up with a Kb equal to 1.3 times 10 to the negative eighth. So that's the Kb for this ammonia, given the concentrations that I have in front of me. We can use the same fundamental Kw expression to be able to solve for the concentration of H plus or OH minus if we happen to know one of them. For example, in this situation, I know that the concentration of my hydroxide is 0.001 molar. In order to be able to find the concentration of H plus, what I'm going to do is use my Kw, which is equal to H plus times OH minus, to be able to solve for the unknown, the concentration of H plus. I take the Kw, I divide it by my concentration of hydroxide, and I get my concentration of H plus, which is 1 times 10 to the negative 11th moles per liter. So again, I've used the concentration of OH minus that I've been given, along with the Kw expression to find the concentration of H plus. We can also use that Kw expression to convert between Ka and Kb. And we actually do it in much the same way. So remember back to Hess's law kind of ideas, where when you combine the Ka and Kb, we get H plus and OH minus remaining. Ka times Kb is equal to Kw. So if I'm going to convert between Ka and Kb, I'm going to do it using Kw. Kw is equal to Ka times Kb, and if I'm given, in this case, the Kb of 1.7 times 10 to the negative 6th, what I'm going to do is I'm going to take my 1.0 times 10 to the negative 14th, divided by 1.7 times 10 to the negative 6th, and I get my Ka of 5.8 times 10 to the negative 9th. So again, I can use Kw to find concentrations of H plus or H minus. I can also use Kw to find Ka or Kb. The last thing I want to talk about are pKa and pKb. Now, just like pH is the negative log of the concentration of H plus, and pOH is the negative log of the concentration of OH minus, pKa would be the negative log of Ka, and pKb is the negative log of Kb. So oftentimes we will see pKa or pKb, and I just need you to understand that finding the Ka or Kb and converting it to pKa or pKb is just as easy as pH or pOH. For example, if I've got a Ka value that is 4.2 times 10 to the negative fourth, and I need to find the pKa, what I'll simply do is do the negative log of 4.2 times 10 to the negative fourth. That's going to give me my pKa value of 3.37. So again, just like we go from H plus concentration to pH, OH minus concentration to pOH, we're going to use Ka and Kb to find our pKas or pKbs. You might not always see it, but it's good to know it just in case you do. So that wraps up today's video. Let's recap. Today we learned how to use H plus and OH minus concentrations along with Ka and Kb to be able to convert between the Ka, Kb, H plus, OH minus, and pKa and pKb. all of these are predicated off of the same basic kW connection. And remember, that kW is constant at 1 times 10 to the negative 14th as long as you're at 25 degrees Celsius. Outside of 25 Celsius, that K value changes. But at 25 Celsius, it's always 1 times 10 to the negative 14th. As we go forward, we're going to be using this concept a lot. And you need to be able to convert between these values with great ease. Today's video was written, directed, produced, and edited by Gavin Cox. Thank you all for watching. I hope you enjoyed it, and I'll see you in the next one.